All right, so today is Friday, thank God. Friday, January the 15th. We have a long weekend with Martin Luther King Jr. holiday tomorrow, on Monday. And so it's all good. I'm excited about that. So today, just to start with, I realized yesterday that when I was going over this first problem 44, I just did A and B, and I forgot to do C and D. So you can just kind of check your work, make sure on number 44 out of the book problems that you guys turned in the other day, that you got the correct answer, you know how to do that. The biggest thing on these problems that I, again, always want to stress is that when you have this heat of reaction, it's always going to be per 1 mole of O2, per 2 moles of CH4, per 2 moles of CH3OH, okay? So that's my conversion factor. These are stoichiometry type enthalpy problems. And so this is always, that's why I kind of put it in purple just to kind of highlight that you have to, it's not per 1 mole, it's per whatever the coefficient is in front of whatever compound they're asking for. In part C, they're asking for the CH4, okay, how much kilojoules how much CH4 gets produced when 82.1 kilojoules reacts. And so we're having to use the coefficient for CH4. In this one, we're using the methanol because the question is talking about the 24 grams of methanol, okay? And then this one is the reverse reaction. It's how much methanol can be made when this reacts with oxygen. And so it's the reverse reaction, so we had to change the sign. It's the only thing that's going to be different is the sign is different, okay? So I just wanted to make sure you all had that. Those of you that are watching this at home, I did just repost yesterday's part 3 video, so you can go back to yesterday's post and click on that one. It's no longer green, but it also is no longer edited, so there's a lot of pauses in it, which you guys watch it at 2 times anyway, so you're already fast forwarding. But today, we just did the thermite reaction. Okay, the thermite reaction. And if you look at the notes that I gave to you on page 8, they need to make LED projectors so they just come on, you don't have to warm them up. All right, so on page 8, it has a thermite reaction. And you can see that that looks, eventually, you'll be able to see, that looks just exactly like we just saw. And for those of you that are at home, I'm going to post a video of this from what it looks like. Okay, so you won't miss out on the fun that we had today. Okay, so notice here's the reaction. Okay, aluminum solid, and for us, we took 80 grams of this, and I took 120 grams of this. I upped it this year, and then 400 grams of this. Okay, so it says this problem says using the enthalpies of formation, calculate the standard change in enthalpy for thermite. Okay, does anybody remember the heats of formation? What is the heat of formation? The name itself kind of describes what it is. Nobody remembers heat of formation at all? It's the energy that's released or absorbed when 1 mole of a substance is made from the elements in their natural state. Now, what's the heat of formation of all elements? 0. Okay? But for this one, it's going to be how much energy when iron and oxygen combine to make Fe2O3, how much energy is released or absorbed, positive or negative, and the same thing for the aluminum oxide. So we can just do the delta H for this, of the reaction, is going to equal the sum of your heat of formation of products minus the sum of your heat of formation of reactants. Okay? So we go to the back of the book. Products, this is 0, so you go to Appendix C. So somebody turn in the book to page 1100 in the textbook, Appendix C, and find out what the heat of formation of aluminum oxide solid is for me. Okay, this value is always going to be given. You're never going to have to memorize any of this. Okay, you always just be able to use it in the chart. But you need to know the heat of formation is the energy that is released. So page 1100, Appendix C. It should be in alphabetical order, AL203.
That is negative 1,669.8.
1,669.8 kilojoules. And it's just 1, okay? Plus 2 times 0, and you don't have to show that. I'm just making a point that the heat of formation of the elements is 0. Minus the heat of formation of reactants is 2 times 0 again, plus what's Fe2O3 solid?
Negative 822.16.
Okay? Now it's just 1 times that, but just to be consistent. I didn't put the units on any of that. Well, I did on those. All right, so so it's just going to be this plus this. So it's going to be the difference between these two. So the delta H of the reaction equals I'm going to say negative 8.
Negative 847.64.
And that's going to be per 1 mole of this being reacted or 1 mole of that being formed. AP does this per mole reaction, just however the reaction is, that's what it's going to be per mole of. Okay? So this much energy is released, it's negative. Now let's do a little bit more complicated problem. Let's just see how much energy was released in the reaction we just did outside. Okay? First off, if I have 120 grams of this and I have 400 grams of that, what type of problem is this? A limiting reactant problem. So the first thing we have to do is determine the limiting reactant. And how do we do that? Do we remember? 120 grams of aluminum times 1 mole over 26.99998. Okay, and we do the same thing with 400 grams Fe2O3 times the molar mass is 55.8 times 2 is going to be 111.6 plus 48 is 159.6. Okay, so what does this come out to? Somebody, 120 divided by 26.98. 4.45 moles, and then what do I need to do with that? Divide it by 2. So it's going to equal 2.225, so 2.23. And this one, 400 divided by 159.6, 2.506 moles. Okay? So which number is smallest? The aluminum. So this was my limiting reactant. So I'm going to start with 4.45 moles of aluminum. And I know that this is the heat of the reaction, negative 847.64 moles per 2 moles of aluminum. So I can say negative 847.64 kilojoules per 2 moles of aluminum. So what does that come out to?
Negative 1,885.999.
Negative 1,800.
85.
Okay, so really we have 3 sig figs, so we can say 1890 kilojoules. So that's how much energy was released. 1890 kilojoules of energy was released, but the fact that it was released in what, 3 to 4 seconds is what, so, and the heat was kind of all trapped inside of there, and so that got the whole reaction vessel super, super, super hot. Okay, so this is kind of a combination stoichiometry from just doing normal stoichiometry, limiting reactant, but now all we do is we just use our heat of reaction as a conversion factor to go from moles to kilojoules. Rather than using molar mass to go from moles to grams, we use that delta H to go from moles to kilojoules or kilojoules to moles. But it's always per how it's written. Okay? So, that's what we just did. It's pretty cool. Mythbusters, I saw one on there where they did this and they cut a car completely in half using thermite. They used a ton of it, and they just had it all in a line over the top of the car, and then they had it somehow where it, like in a bag or something, to where it's stuck to the side of the car, and they just, it was really quite impressive. And so, anyway, very, very fun. I was always scared of this, and so, I don't even know if I still have one. Here. Okay, so when I first, right over here.
Okay.
When I first was reading about this on the internet, okay, I was scared to do it because I'd never done it, and I knew it was super high energy and whatever. So I watched a video of it, and so they said to use 15 grams of aluminum and 50 grams of iron oxide. Well, that fit into this pot, okay? And so I was all excited. We all went outside, and I did the exact same thing we just did, and just go that way, okay? And so we did the reaction. There's a stapler right there.
I don't know if you want me to use it or not.
Oh, and so it lasted like, it was just that was it. I said, all that build up for that, and so the next year I kind of like doubled it or tripled it, and it was still, then it was, and then it was done. So each year I just kind of keep upping it and upping it and upping it, but this is 500 grams for this bottle, okay? We used 400 grams, okay? And this bottle cost about 26 bucks. So, then the aluminum, and then I got to buy the. So this is a relatively expensive, and I have to keep buying new cookie sheets. So it's an expensive demo. However, it's a fun one. It's a good one. It's one of my favorites. So, all right, you guys like it?
Yeah.
Okay, it's better than seeing it on YouTube, I promise. Watching it live. Okay. So the question is this: why is a reaction like thermite so exothermic, so spontaneous, so, just happens all on its own and just bam, goes fast? Other reactions, like this paper right now, is burning spontaneously, but just very, 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 very slowly, as is evidenced over a very, very long period of time. My college notebook, it looks like it's been in a fire, but it's just old, and really old. That's scary how old it is. So, what causes reactions to occur? Why do some reactions occur and others not? Now in this beaker right here, I put some hydrochloric acid. I'm going to put it into this graduated cylinder. So if I take a piece of magnesium metal and drop it down into here, okay, it immediately begins to bubble and fizz. So the reaction is occurring, and bubbles indicate what? A gas is being produced. So when I go, ooh, it's hydrogen gas because it caught on fire. Let's see if we can get a little bit better noise. Not really. Okay? But it's reacting vigorously. Gas is being produced. Okay?
Why'd you put a lid on it? And then
Well, because we need it to mix with oxygen. Feel the right where the reaction is taking place. What is it? Is it warm or hot?
pretty hot.
It's hot. Okay, let's get a girl's opinion. Okay, you gotta say it.
Yeah, what do you think?
It's pretty warm. Okay? So does that make it an endo or an exothermic reaction? Exothermic. Now, if I take this exact same acid, okay, and I take the wedding ring, my wedding ring from my first marriage, which I,
Alright.
and I put it into this same acid.
I was hoping it was.
Yeah, well, I kind of was too, but. Okay, it's made out of gold because it's supposed to withstand any troubles or tribulations that come through, but you know, life tells us that's not always true. So I'm hoping this one is a little bit better quality. So nothing's happening though. So why does magnesium react with the acid spontaneously, yet the gold does not? What are the driving forces that cause a chemical reaction to occur? That's what we want to look at today. Okay? So there are two, bring that back over this way, maybe just slide it over some too. There are two driving forces for chemical reactions. Two driving forces. The first one is energy. And sometimes we call these, by the way, reaction tendencies. AP likes to call it sometimes a reaction tendency. All right, it's just what causes chemical reactions to occur, what's driving them, what makes some happen and some not. The first one is energy, and that reactions tend to go to a state of lower potential energy. Lower potential energy always means more stable. So what type of reaction goes to a lower potential energy state? Endo or exothermic? Exo, because the heat being released to the surroundings, right? So the products have less energy. So exothermic reactions are favored by nature. Okay? And we can, again, use our temperature, reaction progress, actually not temperature, potential energy, reaction progress. And we have the graph that's classic, like this. So we have reactants, we have products over here. Who remembers what that is?
Activation.
That's your activation energy, okay? This is what I needed to do. This is what I had to use the magnesium to start the thermite reaction. Okay, I had to use and get a high temperature to get over it, because it's got a high activation energy. But once it started, then it released a whole lot more energy than I had to put in. Okay, so my delta H is right here. This is my delta H of the reaction. Notice products have less energy than the reactants. Nature favors an exothermic reaction. Okay? And lower energy always means more stable. Okay? Lower energy always means a more stable state. So everything always, again, that's the same thing we talked about electrons. Electrons use heat or electricity, get promoted to a higher energy level, but then they naturally, spontaneously come back down to the lowest ground state energy level. Everything outbound principle, you're going to feel the lowest energy. Things want to be in that low potential energy state. That's the favored state by nature. But we know if I take some baking soda I need my ring back. Okay, so if I take some baking soda and then take some of this same acid and pour it into here, okay, now, hold on, feel this now. It's back to normal temperature, right? Okay, we're all convinced that Advite can tell me that it's normal temperature?
Honestly,
All right. So, normal temperature here, this is just a solid, and I put this in here, and you've all seen this. This is the volcano, okay, reaction. Lots of bubbles indicating what's being produced, a lot of gas being produced. So this reaction is very spontaneous. I'm not having to do anything to it to make it occur. Trying just to keep it under control. Now, feel the beaker. It's kind of cool. It's not freezing cold, but it's cool. Right? So the girls confirmed Advite that it's cool, okay? Which makes it what type of reaction? Endothermic. Which means, on my energy diagram, I'm doing this. This is my products. This is my reactants, okay? I still had an activation energy, but it must have been pretty low because there was enough energy at room temperature for it to just react. But the products end up having more energy. So this is an unfavored reaction. So there must be some second driving force causing a reaction to occur. And that second force is entropy. We use delta S for entropy. Now I have no idea. I've tried to research it. Nobody knows why they use S for entropy, but they do. Does anybody know what entropy is? Chaos. It's a measure of the disorder of a system. Okay? The measure of the disorder. I'm going to put that in purple. Not the order, but the disorder of a system. Okay? So it's a measure of the how many particles you have, how fast are they moving, the measure of the chaos. So in a solid, liquid versus a gas, okay, if I have my solid, if I have a solid, what do we know about order? Is it orderly or not orderly? It's orderly. But when I melt it, then the atoms and ions can move around. We lose some of that order. They're still stuck right next to one another. But then when we create a gas, they become totally apart from one another in total random motion. So what happens to entropy as you go from a solid to a liquid to a gas? It's going to increase. So gases have a higher entropy than solids or liquids. So nature, the second law of thermodynamics says does anyone remember what's the first law of thermodynamics? Okay. We've used it, we just may not have written it down officially, but that's the Q loss equals negative Q gained. Energy is neither created or destroyed, it just changes form. That's the first law. The third law is the whole idea of absolute zero. Okay, that there's the lowest temperature in which you can get to. Second law of thermodynamics is this entropy principle. When a system let's change. Hold on. I'm sorry. I'll just do it this way. Nature favors reactions that increase the entropy of the universe. Increase the entropy. We can say the entropy of the universe is constantly increasing. Well, they're trying to gain chaos, okay?
Gain chaos.
Right, so in other words, when I put the magnesium metal into the acid, it was exothermic and it produced a bunch of gas. That was two really good things. But in this reaction with the baking soda, the energy change was unfavorable, it was this, but the fact that it produced a bunch of gas created the entropy, so that drove that chemical reaction. If we have an endothermic reaction that doesn't produce a bunch of gas, those are the ones that don't occur. Those are the ones that don't happen. There's nothing driving the reaction to happen. So it just sits there like my gold ring in the acid. So, the entropy of the universe. So the entropy of the universe, delta S of the universe, is going to equal delta S of the system plus the delta S of the surroundings. Delta S of the surroundings, delta S of the system. Okay, so we're going to measure the delta S of the system. That can go up or down. That can increase or decrease. But the overall entropy of the universe is constantly increasing. Eventually, everything is turned into useless heat, where molecules are just spread out, randomly moving, and that all things eventually turn into heat. Now, we're constantly being resupplied the energy by the sun. The sun is what makes our earth live. It gives photosynthesis to plants, creates the oxygen, and creates the energy. Everything that we need the energy starts at the sun. So we're constantly having that energy, but the energy is being used, doing chemical reactions, it's producing heat. For instance, and some people even believe that time is related to entropy. Because if you video a basketball dropping from a high height, the first bounce is not quite as high as where you dropped it from. Then the second bounce, and you can see it going down because some of the energy, that's the kinetic energy, is being converted just into friction and heat as it hits the ground. So it loses some, so it doesn't have as much to bounce up. So that useless heat, now the air molecules, that can't be harnessed for anything. It's just contributing to the entropy of the universe. Okay? So if you play that in reverse, you know as the ball is bouncing higher and higher, you know it's going backwards in time because entropy is decreasing instead of increasing. So I don't, in my age, time starts really kind of becoming very difficult to kind of remember how long it's been. But in my early years of teaching, it was thought that the universe, well, it's still thought the universe is expanding, but they thought that it was slowing down. And that at some point, gravity was going to be able to stop the expansion of the universe and then make it start coming back in. Now, there's a couple of curious things on this. Number one, if the universe is constantly expanding, and the universe is everything, what is it expanding into? You know, is there endless space out there for it just to keep expanding? You know, it is the universe really just undefined, and we just have this one. Everything started in this theoretical singularity, this little mass, okay, which I've heard anywhere from the size of a pinhead to the size of a baseball, okay, that all the mass of the universe, all the stars and everything was in that tiny mass, which is very difficult for me just to fathom in the first place. And then there was an explosion, and they went all into these super subatomic particles. Then they all started coming together, and the world as we know it, just out of that chaos came. Okay? I personally believe that God said, let there be light, and from light, E equals MC squared, all matter was created. So there was a big explosion, big let there be light, bam, and then things just all started getting formed. But scientists aren't allowed to use God, so we say that there was a big bang. Okay? But the second law of thermodynamics says that when nature favors disorder, so when things are left to themselves, if you look at a house that's been abandoned for a while, you can see that the house, grass is growing up, the paint's peeling off, maybe the shutters are kind of dangling. It just looks in disarray. It just naturally goes to chaos. Your bedroom, okay? You were told on Saturday, you're not going anywhere until your room is clean. I don't know if you've ever heard that before. Okay, I said it many a times. It was kind of a useless, anyway, my kids do not know how to clean. They still don't know how to clean. But you have to do all kinds of work to get that room in order. You got to look under the bed and get all those socks and things that get under the bed. You got to, hang up all the clothes that you tried on but decided you didn't want to wear. Get the shoes back in the closet, wherever everything goes. And so you do a lot of work to get the room all orderly. And then, daggone it, all on its own, without even trying, it gets all messed up again. All right? And so that's the entropy principle at work. Things left to themselves tend to disorder. So I struggle with how can scientists believe in a big bang where you have this explosion, this chaos, and then out of the chaos, all of a sudden order came to be of our solar system, and then even on the earth, and then just, life itself. When you just look at how complicated the human body is, it's just, the second law of thermodynamics says that things go from order to disorder, not disorder to order. This is my last thing on this, is that I always think of it like you have Main Street America, and you have a hardware store, a paint store, a flooring and carpeting store, an electrical supply and lighting company. They're all right there in a row. Or you could just say it's Home Depot because they have everything. And a tornado comes in and just goes right through the middle of the town and just starts throwing everything just up into chaos out of those buildings. So you got nails flying, you got wires flying, you got shingles flying, you got carpet flying, you got everything flying, paint flying. But when the tornado settles, what's left is this perfect house with nice white house with, green shutters. Okay, the electricity is all run in the walls, the plumbing is all working perfectly, and it's just this perfect house that came out of the chaos. Now, the laws of probability say that can happen. But it's about the same chance as me winning this Powerball lottery. Okay? It's like, it's not a very high probability. But if there's enough time, then you can have a chance to work through all the probabilities and things can happen. And so that's what scientists say, is that it's just a probability, if we have billions and billions and billions of years, that eventually those probabilities can work themselves out and we can, you know, have the order coming out of the disorder. I just think that there has to be a bigger purpose than chance and circumstance for us to be here on earth. That's just my personal belief. You can believe whatever you want to believe. But I just believe the second law of thermodynamics. I struggle with Big Bang Theory with the second law, because things tend to disorder. That's the big thing. All right? Now, so we can just continue on with this. In terms of entropy, the entropy of solids is less than the entropy of liquids, is less than the entropy of gases. We already kind of talked about that. So, what drove this baking soda reaction to occur? Energy or entropy or both?
Entropy.
Entropy only, because the change in energy was endothermic. But what about the magnesium in the acid? Why both?
Because gas is being produced, so there's increasing entropy and energy.
Okay, so they're both being produced, so both changes were favorable, so both things were driving the reaction. So sometimes you can have just energy driving it, sometimes you can have just entropy driving it, sometimes you can have both, but then sometimes you can have neither. And the ones that have neither driving force are the ones that don't occur at all. You've got to have something. You got to either have a lower energy or a higher entropy if the reaction is going to occur. Okay? All right. General things about entropy. Just some general statements. See if I can make sure I get all these in here. Entropies of more complex molecules are larger than the entropies of simpler molecules. Okay, so the entropy of C8H18 is going to be greater than the entropy of CH4. Okay, I should delta S. Okay, if we look at C12H22O11, it's going to be greater than C6H12O6. There's just more electrons, there's more molecules, there's more motion, there's more vibration, the more complex. Okay? Diamonds are a three-dimensional covalent network, is greater than graphite, which is a two-dimensional. Well, pardon me, is less than. Okay, I did this both signs wrong. Okay? Oh, no, that one's right. This one's wrong. Diamonds are more ordered than graphite, because there's a three-dimensional versus a two-dimensional covalent network. Okay? When solids or liquids dissolve into a liquid, what do you think happens to entropy? Goes up or down? Do you have more or less chaos if a solid goes in and dissolves? More, because the molecules break apart and the ions dissociate, so you have more random motions, so entropy increases. But what about if you dissolve a gas? gases are dissolved, like CO2 in water. Gases are dissolved into a liquid. What happens to entropy? It's going to decrease because the gases are losing randomness. All right, last one. We gotta throw lattice energy in here because lattice energy deals with everything. Entropies of ionic solids. Entropies will become larger as the attraction of the ions becomes weaker. Between the ions becomes weaker. So we're going to say, use Coulomb's law. Okay, as an example, we could say NaCl has a greater entropy than MgO. +1, -1, +2, -2. This is stronger lattice energy. This is greater lattice energy, lesser lattice energy. So that means a weaker attraction. So it's going to have the higher entropy. All right, so these are just some things we know about entropies. Okay? Last thing. I think I said that on this one, but this is the last thing. Okay? In a reaction, the sign of delta S can be determined by comparing moles of gaseous products minus moles, and it's got to be gaseous reactants. Now, by the way, we're in chapter 19 now. We're making a quantum leap to the back of the book. So based upon this, if we look at number 43 in your textbook, okay, it says predict the sign of the entropy change, okay, for each of the following. So all we have to do is we look at gases. We have 4 moles of gas in the reactants. We have 2 moles of gas in the products. Now it's going to be 2 minus 4, so it's going to be -2, which means entropy is going down. But you can just do that. Just if moles of gas increases, entropy is increasing. If moles of gas decrease, entropy is decreasing. Okay, you don't worry about solids, liquids, aqueous, only gases. So if I look here, I have 0 moles of gas to I have 1 mole of gas. So what's my sign? Positive. Entropy is increasing. So we can very easily, multiple choice question, easily identify the sign of delta S just by comparing, are we producing gas, or is gas going to something other than more gas? Okay, so it's a really easy, so we have 3 moles of gas going to 1 mole of gas. It doesn't matter big or small. You just compare moles of gas. 3 goes to 1, which means entropy is decreasing. All right, so we know that solids have lower entropy than liquids and gases. I know if I dissolve something, it's going to be an increase in entropy. So again, if I take okay, I just take some water. Again, add by the outside of the beaker. Just basically room temperature, right? But if I take some ammonium nitrate, okay, NH4NO3, and I put it in here, and I give it a good stir,
It's going to think that it's going to.
okay, and I give it a good stir, it's not doing what I want it to do. Yeah, that's good. Okay, we're running out of time, but now feel this.
It is cold.
It's cooler. So the ammonium nitrate is very soluble in water. Yet it's an endothermic process. So why is it dissolving? Because in a solid state, you have NH4 surrounded by NH3 and a crystal lattice structure, an organized structure. You put it into water, the ions dissociate and get randomness. So the dissolving of most solids it's a positive heat of solution, but they still dissolve because of the increase in entropy. It's an entropy-driven reaction. Okay? So we're going to learn how to calculate entropy, delta S. It's going to be products minus reactants, just like delta H. And then we're going to talk on Monday about this thing called Gibbs free energy, delta H. Pardon me, delta G. And see how that kind of is the ultimate determiner whether a reaction is going to occur or not. All right? Y'all have a great long weekend, and I will see you on Tuesday.